welcome everyone, and we're going to be continue our discussion on the hands-on machine learning textbook. And this is chapter 3, which is titled Feature and Target Engineering. Okay, so these are some of the learning objectives that are aligned with the main sections of this chapter. The first one is target engineering. Then we're going to talk a little bit about how to deal with missing values. Then we're going to talk about feature filtering. All right. In other words, feature filtering, that means also to feature selection and some methods that are used to try to get the best features for our model. Then we're going to talk about numeric feature engineering, then categorical feature engineering. Those are the main two data types that we have to deal with them. Then just a little bit of dimension reduction, because dimension reduction is, it could be a chapter by itself. So we're going to just, talk, some introductory concepts, and then kind of an example of a proper implementation according to the textbook. Okay, so let's start with the first section, target engineering. So in terms of not only target engineering, but feature engineering, I remember this quote from Professor Andrew Ng. He's a professor in the University of Stanford, California, and he has a very popular online course called Machine Learning. And one of the quotes that I stumble upon, not in the course, but during a video, is that he says that applied machine learning is basically feature engineering. And since I was, when I got this quote, I was kind of, a beginner in the area of data science. But as you go along in this journey of trying to understand more about the data insights, mechanisms that you can apply, correctly to the data, and also learning about different algorithms that are, today we have a whole bunch of tools to get a model, to develop a model. I've come to realization that what he says is really, is really insightful, because there are only 2 steps that you can really improve your model in this, software development process. The other one, apart from feature engineering, the other one is hyperparameter tuning. But feature engineering is really key, because we are dealing with really applied math here, okay? So the algorithm is going to interpret what you give as inputs, to that model. If the inputs are not aligned or are not designed to get the maximum result of the algorithm probably will perform poorly, okay? So we have to make sure that we just not understand what is the intricacies of the data set, but also in a way try to transform and try to optimize that data set, so that when we give it to the algorithm will then provide the best optimal results. So that's basically what it is, feature engineering. Getting a quote from the ChatGPT. Okay, I did this exercise, okay, to see what ChatGPT tells us about feature engineering, and that was the question: what is feature engineering? And this is what ChatGPT says: Feature engineering is the process of selecting, extracting, and transforming relevant features from raw data. In other words, from data that we collected from one source or different sources, but that is still unrefined, okay, that raw data. So we're going to select, we're going to extract, we're going to transform to create a more informative and suitable input for machine learning algorithms. As you will see, some algorithms, for example, our traditional regression model, linear regression, or sometimes it calls ordinary linear regression, it needs a certain kind of inputs to try to make the best of the output that that model is going to do. And we're going to speak about some of those assumptions. Some other algorithms needs the data only in numeric format. So anything that is not numeric has to be converted to numeric. So those are some of the examples that we're going to see that it's necessary, in fact, it's mandatory to do this with this process, feature engineering. Also, the ChatGPT says that it involves identifying, right, the most important characteristics of the data and representing them in a way that is compatible with machine learning model input scheme. Okay, so again, the different algorithms, okay, linear regression, decision trees, neural nets, they expect a certain kind of inputs, okay? Because if not, they're not going to understand it. So that's why, at least in that sense, it's important to do this feature engineering. But also, you can do a lot of transformation to that raw data and create new features so that your model can perform better, okay? Can be optimized, you know, to the result that you are looking for. Okay, so let's get busy with the target engineering. So target engineering, what it refers, and this is more in the domain of the supervised learning. You know, when we talk about supervised learning, we are saying that we're going to build a model where you are going to predict the outcome, okay? And that outcome is already labeled in that data set. So for this example, we're going to use the AIMS housing data set, okay? That's a very popular data set. In fact, you know, there's a course in Kaggle about linear regression or regression methods that uses this data set. So when we look at this data set, we already did some of the, you know, pre-processing, the splitting process. When we look at the training data set, okay, in the last chapter, we talk about splitting the data set into training and testing, etc. When we look at the first 10 variables or columns, the first one that is going to appear, at least in this particular, you know, order, is going to be the sale price. And the sale price in this example is the target, okay? So the data set is a bunch of information about housing units. And then what we're going to do is predict the sale price, okay? So one of the first things that we have to, you know, do in our exploratory data analysis is try to understand what is the distribution of that target, of that outcome. So for that, because the outcome is numeric in this case, all right, we can use a histogram. Okay, so using the ggplot package, we are going to display, right, a histogram, which is a picture of the distribution, how those values in the sale price are distributed. Okay. So one of the things that we can see here is that there is a kind of a maximum concentration here in this particular a value here, okay, which usually we call the mode. Then it starts to taper off, but as you can see, there is a long tail here. Okay, there's a long tail. So that means that the distribution is kind of skewed. It's skewed to the right. Okay, and also implies that distribution has some it could have some outliers. Okay, and we can see in the in the last values kind of a flat bend there. We can see that there's a value that kind of departs from the rest of the concentrated value. Okay, so to get a more numeric sense as that of the skewness, we can use this library called library moments. And then with the skewness function, we can input that vector, the sales price, that vector into that function, and it will give us a number. Usually, a Gaussian distribution, what we call a Gaussian or normal distribution, the skewness is going to be between -0.5 and 0.5. Okay, that's the basic the tolerance of that distribution. Anything beyond that means that there's a skewness that we have to take in account. So in this case, the number is 1.67. So because it's positive, it has what is called a right skewness, as we see in the histogram. So that means that the majority of distribution values are left of the distribution mean. In other words, they are around this, this area. Okay. All right. So what are we going to do? Well, the ordinary linear regression model assumes that the residuals, okay, the errors between the outcome and the predictions, they have to be normal distributed. One of the things that can affect that assumption is the distribution precisely of the target. So one solution that we can do is to normalize, right, with a log transformation. So what we're going to do here is apply a log function to the sale price, so that then we can compress that range of values. We can compress it to a smaller range of values and try to get all those values, try to get it to behave as a Gaussian distribution. So if we apply that and just looking at it visually, we can see that before we have this right skew, right? Now we have some some values that are of the distribution, but more or less you can see that the distribution is more Gaussian, more normal than the original. And if we apply the skewness, right, the skewness function that we applied before, we get now a value of -0.09. So from 1.67 positive, we get a -1. So in other words, the skewness is going now to the other side, but still it's an improvement from our untransformed value. Okay. Then another method that the author mentions is to apply, instead of a log, is to apply a box-Cox transformation. And for that, let's go to the source, right? Let's go to the source here, and this is the transformation here, okay? So what it's going to do, because box-Cox doesn't accept negative values, okay? So right now, the sale price, if you do like a summary, a summary statistic, you'll see that the minimum value is going to be a positive value. So the box cogs, can handle this, this range of values. And what it's going to do is going to apply, if the lambda is not 0, it's going to apply this function. If the lambda is 0, then it's going to apply the log. Okay, it's going to revert to the log. So going back to our histogram, when we apply the box cogs, we also can see that even though the log, there were some outliers, especially to the left side, here in the box cogs, they're going to be, the transformation is going to try to get it to a Gaussian distribution, but it's going to leave some outliers to the left and to the right. And if we apply the skewness function, then we're going to see that the skew is a little bit higher than the log transformation by itself, 0.2. So if we are going to select which transformation we should do, in my opinion, we should select here the log transformation. Why? Because the log transformation is not parametric. Okay, you don't need any parameter to find the log, and it's very easy then to transform it back to the original value with the exp function. In the case of the box cogs, you need what is called a lambda, okay, which is the parameter that we saw in that equation. And that lambda, eventually, when you're going to inversely transform those quantities to the original quantities, you need that parameter. And that's one of the comments of the textbook. So this one requires a little more engineering, the box cogs, than the log transformation. The log transformation is just the function. So in the comments of the textbook, it says that be sure to compute the lambda on the training set and apply the same value, lambda, to both the training and test set to minimize data leakage. In other words, when you use a box cog transformation, you are going to obtain a lambda, okay, from the transformation. So that lambda is going to be applied not just to the training set, but also to the test set, because remember, the test set also is going to have that outcome, okay? So you need to transform it, so put it in equal, in equal footing. And I added that the recipes package automates this process for you, okay? So if you use tidy models and if you use the recipes, it's going to do it for you. If we don't use the recipes, for example, if you are using other methods, then you have to be very careful to apply those both to training and to test sets. For the log transformation, you just need to apply the log. That's it. So the log right now is more simple engineering, and also it gets better results than right now the box cogs. Also, I mentioned that the box cogs requires that the input variables be strictly positive. So another method that you can use when you have negative values is what is called the Yeo-Johnson transformation, okay? And if you use the recipes package, you can use the step Yeo-Johnson to apply more or less a similar procedure as the box cogs, but it can handle negative values. Okay. Any comments? We're good?
Yeah, yes. Actually, what I'm gonna try to say is, I'm kind of a little bit curious about okay, maybe if we can transform our target variable based on the maybe box and cogs transformation method. Actually, compared to the log transformations, actually these box and cogs transformations seem to be a little bit complicated when we try to interpret the result. So yeah, it is actually very good at kind of when you scroll down, we actually, when we have a kind of a negative value in our target variable, it might be good for the transformation to the box and cogs. But the thing is, like like how we can interpret the result kind of purposes. Maybe log transformation gonna be the much better. Like for
Right.
example, like log y is like a beta 0 plus beta 1 beta 1 x1 and then error term. In that case, how we can interpret this one means like 1 unit, not the 1 unit, like how this one means is uh like a beta 1 in here, and then this one is a coefficient. So
Right.
like to get a 1% change in y is a
Yes.
beta 1 unit change in x, right? So maybe for example like 0.5 means not the beta 1, like a 1 unit change gonna be causes like a beta 1% change in y. That's the
Correct.
how this one actually interprets. So actually log transformation is quite straightforward, right? Like 1 unit change in x gonna be causes in this case is a 0.5 means 0.5% change in y, right? So in case of the log transformation, it is very, like I would say, straightforward.
Yes.
Yeah, straightforward interpretation.
Yes. One thing that I also want to mention is that because the box cogs cannot handle negative values, the same thing applies to the log. Okay. You know, if you try to apply a log to a negative value, it's going to give you something, you know, of an infinity. Okay.
Right.
Because here, you know, it's the exponent. It is the exponent that you are, you know, resulting from the log, right? So to get a negative value from you know, from the log, the result is going to be infinity or, you know, some kind of error. So the same thing applies to the log. Okay. So for negative values, definitively, if you have to transform that target, you need to use this one, Johansson. Okay, is the one that really can handle negative inputs, or you could change the range of that you know, of that target, right? So that all of them are positive. So for example, you can change the range from, let's say, -5 to 30 to get them all to 0 to 1. Okay. And then because 0 to 1, then the log can handle it. The only thing is that you're going to add 1 plus 1. Okay. So that way also you can, you know, you can manage it. But the Johansson usually is the way to go if you have, you know, negative values. Okay. And of course, this is when you have the need, right, to transform that variable, because if your variable is behaving like a Gaussian distribution and you do all your, you know, statistical tests and you feel comfortable with that, then maybe you don't need to do this. Okay. It's when you have certain behaviors in that distribution and some of the algorithms are telling you, hey, you know what, I need this more in a Gaussian way. Okay. For example, tree-based algorithms, they don't need this. Okay. They can handle the target distribution as it is. Sometimes it helps also, you know. So, you know, you have different opinions in terms of using algorithms that they don't assume that the target has to be Gaussian or normal. Okay. So there's a lot of you know, there's a lot of alternatives here.
Yeah. And also maybe I would like to point out that other than the log and box-Cox transformation, we also thinking about in the regression model, there is also alternative called maybe we can try to do the square root, scale roots kind of things,
Yes.
right?
Yes.
And
Yes.
also the other thing is we can also transform like a G-score, like sigma and y minus maybe mu a y. So this is also
Right.
gonna be easy to interpret to get the result. And also the other thing is also we can transform into the 0 to 1 kind of a
Correct.
transformation, like y minus, I think that 0 and then y minus 1, I guess. I don't know, like this.
Yeah.
Like yeah, 1 minus y. Yeah.
Yeah.
It's
It's
a
kind of the min and max. Okay.
yeah,
You have
min
to
and
do with the
max.
min and
Yeah.
max there.
Yeah, min and max kind of method. Maybe
Right.
it might be the 100, but like a scoring system. So these are the also kind of all of the different kind of method is the very allows for the more straightforward interpretation of our result. Yeah, so
So
yeah,
that those transformations we're going to be dealing with them with when we talk about numeric
right.
because that also doesn't apply not only to the target but also to the predictors too. Okay.
Yeah, right.
Okay, so let's continue. Okay, let's see what's the time. Okay, so probably we'll have another session to complete this because I see the time is 7:27. All right. So dealing with missingness or missing values. So this is a whole chapter in some of the books. In fact, there's some books that only deal with with missing values. But this is more or less to give you the awareness that some algorithms expect a complete data set. In other words, that there cannot be any missing values in your data set. So let's take, for example, again, the Ames housing. And this time we're going to use the raw, okay? The raw data set, which contains, of course, missing values. So one quick insight that you can get is to see if your whole data set anywhere has any missing values. And with this command from is.na, which gives you a Boolean, okay, for true or false, true if it's missing value, false is not. And then you can do a sum, right? Because true is going to translate to 1, false to 0. So here we see that the raw data set has 13,997 missing values. So you have a lot there. Okay. So, but where are they? So this one I use, almost every time, I'm exposed to a new data set. It's called SCIM-R, okay, skimmer. And this one provides like a radiography of your data, not only for missing values, but also for how many unique values you have, in a character type data. What are the ranges, okay, of numeric values, etc. So to make it simple, I did a function, okay, with this function skim width. And then what I'm going to do is that I'm going to, get rid of, for now, of the first quartile and the third quartile, just to make sure that the table fits, in our screens. And what I'm going to do is apply my skim function and then filter for those variables that have some missing value, okay? But missing value count greater than 0. So in this one, the Ames row, which is the raw data set, we have all the observations, okay? Now, and we're not dealing now with the training, we're dealing with the whole data set. So we have 2,930 observations, rows, and then we have 82 columns. So this is, quite a dimensionality data set. And here we have the skimmer divides your your data set into variables that are character variables, okay? And also numeric variables. If you have date variables, it's going to put it separately, and also if you have Boolean. Okay, so you can see that in the character, which is kind of a candidate for a categorical, it could be a candidate because some of them are going to be very, the cardinality is going to be very high. So in the character, we see that there's quite a bunch here. For example, a variable called Ali, a variable called pool QC, fence, miscellaneous feature, that have quite a number of missing values. In fact, pool QC, from 2009-30 observations, it has 2,917. In other words, it only has 13 observations that have something there, in that variable. So the percentage in terms of complete rate is almost 0. Okay. And also we have, for example, electrical here that only has 1. So that could be, probably maybe an error or maybe something that skip the information gathering, etc. So this is kind of, easy to manage here. But the ones that are, very high in missing values, we have to see, what we are going to do. Then in the numeric, also it gives you the percentage of missing. And here we see that some of the basement variables, they only have 1. The garage type, and we're going to talk about that, okay, is kind of combined with these ones, with the garage cars and with the garage area. And the lot frontage, which is the measurement of, how many meters, because this is from Iowa. No, maybe feet. Okay, I was confusing with an Australian data set. The lot frontage is the measurement of the front of your lot size in terms of feet. Oh, okay, and that one has 490. So this is a way to picture, your situation in terms of how many variables do you have that contain missing values, and also the magnitude of those missing values. The author uses, from the Nanier package, he uses this function, vismiss, to try to visually, get a sense of where are the missing values and if there's a pattern in them. This one is kind of squish because of the quantity of the variables. Okay, so this one sometimes is good to use when you have, let's say, 20 or even 30, because then you can see clearly, the variables names. Okay, but there's another package that it will give you more insight. In this case, more insight when you have a lot of variables with missing values. This one is called Data Explorer. Okay, and the function is plot missing with missing only true. In other words, we're going to see only the variables or the columns that have some missing values and the percentage. Yes, and here you can see that if you follow the legend here, you can see that, remember those character data types that have a lot of missing values, where they are at the bottom, and the suggestion for the legend is that you should remove them. Okay, that's a suggestion, because we'll see that we can deal in a different way with those features. Then you have fireplace quality, right? Yes, they're just suggestions, to guide you. Fireplace quality falls into the category of bad. Okay, so whatever bad means here. Then you will see the lot frontage, which is the only numeric variable that has, a significant quantity of missing values, and then the rest. Okay, so this one, in this case, I prefer it over this one. Okay, because this one is kind of, it's kind of difficult. to appreciate which are the ones that have, you know, the most missing values or the least missing values, okay, or they are in order. But here you can see some of the patterns. In other words, there's going to be, yeah, it's complicated, but you are going to see there, at least visually, you're going to see that there is a pattern in terms of some of the missing values. Okay, so one thing that we have to make sure that we understand before we do anything, you know, trying to resolve this missing values conundrum, is what is the cause for missing values? And you have to do kind of a research and also talk to your, you know, to your experts, right? You know, the ones that collected the data and the ones that know more about you know, how was the process about, especially when let's say that you are dealing with a survey, okay? So there could be some errors in the data entry, okay? You know, usually unless it's a device, and the device also can generate errors, but if it's a human, we know that humans err. So maybe that's a possibility, okay, depending on how the data behaves. For example, let's take age, okay? Age, some people in a survey won't tell you your age, or maybe they will underestimate your age. So because they don't tell you, and it's a missing value, doesn't mean that that age cannot be known. You know, depending on the population, depending on the characteristics of the demographics of your data, you can do a best guess on what the age of those non-respondents, you know, could have been. Okay. Then values were never recorded. For example, we have a device that records temperature, but that device was out of commission because of maintenance or maybe some, you know, some defect or mechanical malfunction. And for a period, you're not going to see those values. So that explains why those values are missing. And we discussed about the age. We discussed that some respondents did provide a numerical categorical input. For example, if you ask people, do you smoke? Probably, you know, people will say, you know, that's not your business. Okay, you know, they don't give you a yes or a no. So you have to, you know, be very creative in terms of what are the questions in a survey that you're going to, you know, ask to certain population and how you can derive certain information from it. Okay, so how we're going to deal really with missing values. So the textbook gives you certain options, but I'm going to add this chart. This chart is very useful, okay? You know, to get us, to give us, you know, a path in terms of what are the best practices to deal with this, you know, missing values issue. So two things you're going to do with missing values usually: deletions or imputations, okay? In the deletions, you have that, for example, remember that pool feature that has almost everything is missing there? Well, you could say that, okay, from certain percentage of missing values, I'm going to get rid of those variables, those columns. Okay, so you can drop entire columns and, you know, deal with that situation. Also, you can delete entire rows. For example, if a row has a missing value in one of the columns, right, in one of the variables, then we're going to delete it. Of course, remember that this is a 2,930 rows observations. If you start deleting any row that has missing values, and there's some that have a lot, that means that you are going to basically reduce significantly your data set. So sometimes this option is not really, you know, an advisable one, because you are then reducing your number of rows. Okay, so be careful with this one. It's called listwise. Okay, so the pairwise. The pairwise was one that I had a little bit difficulty, you know, to understand. You know, what do they mean by pairwise deletions? In fact, when only, you are going to delete only some missing values. So to give you some insight, I went to this article, okay, dealing with missing values, and it does a comparison between what we have said about the list-wise deletions and the pairwise deletions. So we said that in the list-wise deletions, we're going to delete any row that has a missing value, no matter where, okay? So in this one, we have gender, manpower, and sales. So if manpower is missing, we're going to delete it. If gender is missing, we're going to delete it. And if sales is missing, we're going to delete it, okay? So that's a very radical approach, okay? You're going to reduce, remember, you're going to reduce your number of observations. If there are a million observations and you're not going to reduce, let's say 1% or 2%, well, maybe you can get away with it. But in this case of the Ames housing data set, I don't think that's an option because there's a lot of columns that have a lot of missing values. So you're going to be, taking out good observations because of those columns. But in the pairwise, what we're doing really is focusing on these missing values and then selecting certain variables for statistical, let's say statistical analysis. So let's say that you want to see if there's a change between, in gender, compared to, in sales, sorry, compared to gender. So for example, you can, say how many, what is the range, the distribution of sales taking one gender, okay, male, and then compare it to the female, okay, and do maybe a statistical t-test analysis or a z-score analysis. So in that case, the pairwise deletion, how it's going to work is that you're going to delete only the observations of those variables that have the missing values, okay? You're not going to delete the ones that had any other variable that is not interesting in this instant to you. You're going to delete only the ones that have the variables that you are studying, okay? So that reduces the pairwise deletion, reduces the amount of rows that you're going to be deleting, okay? But this is only applies to that particular insight that you're going to be using certain variables only, okay? If you're going to use modeling, then apart from the list-wise or the column deletion, this one is going to be very, very, very useful, okay? Because you are only selecting certain variables, and sometimes you want to see what is the behavior of the algorithm within the whole data set, okay? Any questions about the pairwise? Because I know, at first,
Yeah.
I was a little bit confused, but then, I started, doing some research, and this is what we came with.
Yeah, right. Because yeah, you're very clear about this, but the thing
Okay.
is that as a kind of like a social science research, how to say,
Yeah.
we actually prefer to the list-wise deletion compared to the pairwise. Actually,
Okay.
pairwise deletion is very, very useful when you try to do the kind of like a univariate analysis.
Yeah.
So that means like okay, among I would say, assuming that all of these column, like gender and manpower and sales, these are the maybe, I would say, independent variable, and then our dependent variable is separate. In that case, we can just try to do the using each one at a time. So sales versus maybe dependent variable, or manpower versus dependent variable, and gender and dependent variable, etc. So that means univariate analysis. Because what is the big disadvantage of this is actually this, because in here, like a different sample sizes. So that means when we try to using all together into the one model, usually R actually gonna be selecting move to the list-wide deletion, not the pairwise deletions, because each column has a different sample size. So and then
Yes.
R tends to be choose the more complete cases. So that actually moves to the list-wide. So list-wide deletion is what is the big advantage of the list-wide deletion is that we actually have a very same. We have the very fixed sample size. So we only use those complete cases.
Correct.
Because so that actually allows us to kind of develop our model and then try to understand some of the association or get some prediction. But in here also says that reduce the power of the model. That is actually kind of a maybe in terms of the traditional statistic purposes, list-wide deletion can be very useful. Anyway, we can just understand the association. But the thing is, predictive regressive purposes reduce the power of the model, which means due to the reduction of the sample size, reducing of the statistical power of model gonna be the critical. Because in machine learning approaches, our goal in regression model is try to develop the more predictive model to when we have a new data set and then so that we can get the more accurate target outcome. Is that correct? So
correct. Yeah.
In terms of the machine learning approaches, like this one, like a machine learning approaches, lose this power of the model gonna be the critical. But the thing is, if we just only focusing on the like a traditional statistic, like understanding the relationship in the model, we usually prefer to the list-wide deletions compared to the pairwise, because the pairwise only allows us to the kind of a univariate analysis, kind of a one-to-one kind of a testing. So t-test, maybe t-test for the sales and dependent variable, manpower versus dependent variable, or some kind of a maybe cross tabulation based on the gender for the maybe for the statistic, etc. So so that's the kind of things that I wanted to talk about. And also the other thing is when you go to your slide. Yeah, because that is actually about the deletion things. And also rule of thumb, actually, I don't know that is also applied to the other academic field or practice. But rule of thumb for this dropping entire row is actually if maybe out of your total observation, maybe the number of row for the list-wide deletion is less than 5% of the entire observation, we can choose this one. That means if we have if you can keep 95% of the complete cases, and then your missing data set is only less than 5%, maybe you can just feel free to say delete entire row and then try to testing to the analysis or try to develop the model. I think as far as I know, 5% is one of the threshold that they're thinking about do we have to do the list-wide deletion or not. Maybe a little bit more loose kind of criteria is up to 10%, you know. So 10% will be kind of okay, but 10% is kind of a little bit dependent about your sample size. So for example, maybe if you have 100 observation and 10% gonna be you only keep the 90 observation. In that case, you have to thinking about the 10% is not good enough. 10% is quite critical, but maybe if you have maybe 100,000 observation, your 10% gonna be maybe 10,000, right? So you still keep the 99,000 data sets, so which is still quite good sample size.
Mhm.
So depending on your sample size, you can actually adjusting this kind of a ratio for your criteria judgment for the list-wide deletions. Yeah, that's the kind of things. So that's what I wanted to talk about.
Okay,
And
excellent.
then are you gonna do the imputation one now?
Yeah, I think that's all we can, all this basically the time that we have left. It's already
Okay.
7:50. Okay,
Yeah,
so
right.
you can deal with the deletions, deleting, some of the information there, to get your data set, completed. But also you can impute. In other words, instead of, going this way, you can go this way, imputations. And there are several, methods that you can use depending on what kind of data set you have. For example, in general, when you have what is called a non-time series, in other words, there's no date, like the Ames housing, you can do imputing with a constant, okay? And you'll see an example of that. And also you can impute with some parameters, okay, from the data. For example, the mean, the median, the mode, okay, or any other common value that makes sense, right, for this particular, for your particular case. In case of time series, you can use forward fill. So for example, you have a sequence of numbers with a date or a time. Then what you do is that the missing values, they're going to be imputed by the value before that is not missing. Okay, so that's kind of a forward fill. The backward fill is reverse. It's going to be the next value that is not missing is going to be then imputed to that missing value. And also you can use interpolation techniques. Okay, this one we're not going to be seeing here because it's more on the subject of time series. Then you have more advanced imputations. For example, KNN, K-nearest neighbors, algorithms that can give you a best guess value or kind of a prediction, right? Or best values of the missing values in terms of the whole, right? Of the whole data set. Also, you can do tree base here, missing values. And there's a technique also that you can use that is called MICE. It's called, this is an acronym for multiple imputation by chain equations, okay? It uses regression models to input numeric and also categorical values. Also, this is going to be a little bit out of scope. So let me see if I have some time to just give you an example of one of the imputations with a constant. Okay, so before we start doing any deletion or any imputing, any missing value, it's always advisable that you investigate what is the meaning or cause. And we have seen this in the question that I said, what is the cause of the missing values. In this particular data set, the ones that created this data set provide a lot of documentation. And for example, they provided this documentation. Okay, let me see if I can put it here. Okay, I don't know if you can see it. Kiantu?
I can see it.
You can see it? Okay. So here you have is, sometimes it refers to the data dictionary, where you have information about each of the columns or the variables and what do they mean. For example, this lot frontage that we know that we have some missing values, it says that it's a continuous value and it is the linear feet of street connected to the property. In other words, the front of the property, right? And it's going to be linear feet. But one of the variables that we were trying to explain was garage type, okay, which has a significant number of missing values. And it says that garage type is a nominal. In other words, it's a categorical value, but it's not ordered, right? Nominal. And it also refers to the garage location. And it gives you kind of a legend, an explanation of which are the values contained in that particular variable, okay? So it says here that the NA, what it really means is that there is no garage. All right. In other words, you can input this value of NA in this variable garage type by saying, you can say no garage, okay, to make it more, more descriptive, or you can say simply none. All right. So it has an explanation. In other words, the NA here means something. Okay, it has information here. The imputing, when we talk about using KNN or using, tree-based imputing, is when we don't know exactly what the NA means. Okay, and we have to, do our best guess, because we cannot, in good sense, try to delete those observations because of certain restrictions. For example, the sample size, etc. Okay, so if we go back here, right? If we go back here to our garage type, missing values, apart from the information that we have from that data documentation, also we can check with garage cars and with garage area. So we see that when we select those three variables, they align perfectly with garage type. In other words, there's no garage cars and there is no garage area. So that means that there is no garage. Okay. So in this case, we can input the missing values with a label, none or no garage. Okay, depending on how descriptive you want to do it. Okay. So let's see. Okay, so let's finish here. Okay. In the imputation, as I said, it's a process of replacing a missing value with a substituted and best guess value. In other words, we don't know exactly what the missing value is for. We have checked documentation, we have done the research, we have talked to the experts, and we still don't know. So one of the things that we can do is estimate the statistic by the mean, median, and mode. But the author of the textbook and a lot of authors say that you should avoid this method. And the reason is that you are distorting, okay, the distribution, the variance of that variable when you use mean, median, and mode. So the best method, at least according to the book, is trying to use a more refined approach using K nearest neighbors, using tree base, or even, you could use mice. The problem is that mice is not available in tidy models recipes. It's just the KNN and the tree base if you want to not input using a known statistic. Okay. So basically that's it for the missing values. There's a lot of theory, a lot of alternatives to do this. Try to use more logic here, kind of a common sense approach. And also it's important to research, okay, your data set, where does it come from? If there's any meaning to any missing values there, or if you can talk to someone that was in that process. Okay.
Actually, this kind of a method we can use. Have you heard of the term for the completely missing at random?
Yeah. MCAR.
Yeah,
MCAR.
and also missing at random.
Yes.
These are the kind of a term we have to understand when we try to do the imputation, right?
Correct.
Actually, completely missing at random is the kind of we cannot find out any patterns. So
exactly.
Yeah, maybe no clear patterns.
Yes.
Of missingness, right? And then when we talk about this one is that there is actually patterns.
Correct.
Of missingness.
For example, an example is that the garage type. That
yeah,
you can
that is
perfect.
Yeah, that is actually
variables. That is
that is actually typical example about the missing at random kind of thing.
Right.
So So actually, when we try to think of the using KNN or tree basis or mice for the regression purposes, regressive approaches.
Yes.
In this case, actually assumes that we actually find that there is a certain kind of a pattern of the missingness, and then we can try to choose the one of these three methods, and then we can, when we have a maybe completely missing at random, which means we cannot find any patterns of the missingness. That
Right.
missing pattern is a completely random. That means we also say that it is okay to do the list-wise deletions.
Yes.
Yeah, because of the pattern of our missing data is completely random. So even if we can try to do the list-wise deletions, that is also highly randomly deletions kind of things. So generalizability of our result from that deleted data set, and also the distribution after the list-wise deletion also gonna be, we can say to assume that that is also a completely random sample from the population, you know.
Yes. Yes.
So in that case, we can just do the list-wise deletion. But in this case, missing at random, we can think about using these things, but still in a kind of a social science kind of a research and practices, we still try to avoid these kind of things. Like actually imputation kind of thing is not kind of allowed to use this in a social science, because social science is highly kind of related with kind of persons. So that means regardless of data is the complete missing or missing at random, it is actually talk about the people and then people interaction to the some aspect of the topic interest. So in that case, we cannot predict, we cannot fill in the blanks from those things based on the patterns of the other people, because every person are different, you know. So we cannot, it is quite dangerous to predict those responses based on these modeling approaches. Maybe we can do that if we can have a feeling to the very small observation, but usually social sciences, we actually do not use the imputation things at all. Actually, imputation is a very useful, like engineering, and then especially for the medical experiments, you know, because in this case is about the non-human kind of things, and then a medical experiment means that there is actually lab kind of environment, right? So actually, researcher can control all of the possible factors that affect to the lab experiments. So in this case, imputation gonna be work very well, you know. But in case of the social science, like deal with the human, it is quite hard to apply to the imputation. So
remember that the imputation is basically, you know, like a last resort, method to try to input the data set into the algorithm in a way that the algorithm can understand it. So, you know, you can do the deletion, you can do that, but eventually, if those are not available for you because certain, you know, size of the sample size that you cannot delete it, because then you're going to be, you know, kind of hacking, you know, that data set basically, and it's no use. Depending on the situation, sometimes imputing, it will be the choice, you know, that you have to proceed, but then you have to make the assumptions. Okay, we did this because of, you know, this particular, you know, situation that we have, and you explain.
Right. So And also the other thing that I want to talk about is like imputations in the social science. We actually deal with the human, and then we cannot understand that their responses to some certain amount of a topic compared to the engineering. Because the reason why we do not use this one is actually most of the social science experiment is what is called a quasi experimental kind of a situation. Because compared to the lab environment, which is a very highly experimental, this one is we can actually control almost everything, right? Not I would say not all the things, but almost everything, because we can control that. But in here, in case of the social sciences, like a quasi experimental research design, we already have a certain amount of the external factors and also settings. Because there is already some kind of a setting, the environment or some factors that already set up. So those are the kind of very baseline information. Right. compared to the starting from the scratch in the kind of a lab environment. So that is also make us very difficult to impute our data set, because there is a lot of factors and already a lot of factors that already set up that also affects to the human response of the human responses to the each observation in social science. So due to these kind of quasi experimental settings or research design actually make us to very difficult to impute our observation to fill in the blank in case of the social sciences. In compared to the experimental case like a lab-based research design, actually these lab-based environmental actually control or develop built by the researchers, right? Like some medical experiment, like to testing the effectiveness of some kind of a medicine, like try to do some testing to the mice, you know. These are the actually totally controlled by the researchers in that lab things, right? It is actually very closed system, you know. So in that case, imputation might be okay, because that is actually very helpful. Because in medical experiments, maybe sometimes due to the kind of human error kind of situations, maybe researchers might missing some steps that affects to the outcome. So in that case, maybe researcher can thinking about adjusting their responses or outcome depending on their context, and then there is a very strong rationale to adjusting those kind of value through the imputation process. That might be okay, but social science, it is very hard to do that. But even if the engineering and medical experiment or medical science to imputation is the very careful. We have to be very careful to conduct the imputation, because without any kind of a very theoretical rationale to support the reason why we use the imputation method, without any strong theoretical or some academic literature review kind of things, it should be very careful to use imputation methods. So mostly in statistical purposes, imputation is not recommendable. That's what I wanted to say. Because even if the highly experimental kind of a situation, we still need to be very cautious when we using the imputation.
Okay, just to recap, we should use these methods, on a case-by-case basis. Okay, because sometimes you want to say, okay, imputation, should not be, used, but there's some cases that merits that. Okay. Also, you can extract some information from that missing variable. For example, not trying to do a plug on the values of the missing value, but using that missingness as a flag. Okay, so for example, you can create a feature that says, okay, the garage type, if we didn't know, the garage type, the NA definition, you can say that, okay, we're going to put 1 where there's a missing value in the garage type and a 0 when there's no missing value. So you can create a flag, and that flag variable can give you some information about your outcome or a combination of predictors. And there, you're not using really deletion or imputation. Okay. So that will be another alternative that you could use, to get information from the missingness of the data. Okay, it's a very interesting topic about the missing values especially in the surveys. Okay.
Like using the flag variable is a kind of like a very useful because this one actually can be used as a kind of a classifying about our validity of the data set for that specific column or observations, and also maybe some kind of using it as a kind of a dummy variable to get us the more income, more info for the outcome. I mean, so
yeah. For example, I remember an article, when I was, researching about the missing variables, not now but before, about a study on the grants. Okay, the certain amount of the grants, and there was a column that said, if you could identify the source of the grant,
right.
You know that sometimes the sources are anonymous, right? In this case, I remember it's about 40%. But what happened is that missingness, give you some information about the magnitude of the grant.
Yeah, okay. Right.
So when the source is anonymous, there could be an effect on the amount of the grant than when it is not. So you can use that information. Okay.
Okay. Gotcha. So actually now it is 8:13. So we already passed an hour.
Already passed the time,
because this one is actually, like you said, chapter 2 and chapter 3 is covers a whole different kind of a very, very fundamental principle about the machine learning in the process. So we have to spend more time to work on and study this a little bit further. So maybe is it okay for you to cover the rest of the section in that chapter?
Next time, of course, the next session.
Okay.
Well, I think we can do it because this one is the one that really, packs more. The other ones are more simple. Yeah.
Okay. So next week we can cover the rest of the chapter 3, and then we can keep moving. So thank you very much. And then today your presentation and then your summary is very, very helpful. And then I can also understand, and then you actually addressed a lot of topic actually, which is very important. So so let's talk about that more in the next week, and then we can wrap up chapter 3 then.
Okay.
Okay.
Have a great Sunday.
Yeah. Have a great weekend, and then see you next week.
Okay. Excellent.
Bye-bye.